Quadric surfaces. Quadric surfaces are the three-dimensional analogs of conic sections. If you remember from pre-calculus, conic sections include ellipses, hyperbolas, and parabolas. We're going to be looking at the three-dimensional versions of those. Here is the most general form for an equation of a quadric surface. We're going to eliminate the cross terms, the ones with xy, xz, and yz. We can always use a rotation to change that into a simpler form. And we're not even going to go into that in this course because it is a little bit more advanced. We're going to focus on quadric surfaces that are oriented along one of the axes. Also, we're going to focus on quadric surfaces that are centered at the origin. It's very easy to translate quadric surfaces basically the same way we do it for ellipses, hyperbolas, circles, spheres, and so on, by replacing x by x minus a, y by y minus b, and so on. We'll look at an example of that at the end of this lesson. In order to sketch the graph of quadric surfaces, we're going to use what's called traces. These are cross sections of the surface in various planes. The cross sections of the quadric surfaces are going to be conic sections. So it's good to just recall a little bit of information about these various conic sections, such as ellipses. The standard form for an ellipse centered at the origin is x squared over a squared plus y squared over b squared equals 1. And to sketch the graph of this ellipse, from the origin, we move left and right a units to get the vertices that intersect the x-axis. And we move up and down b units to get the vertices along the y-axis. A hyperbola has a similar equation to an ellipse, except there's a minus sign instead of a plus sign. The hyperbola x squared over a squared minus y squared over b squared equals 1 has the following graph. Notice we move left and right a units from the origin to plot the vertices of this hyperbola. We won't be concerned with the number b here. It has to do with the asymptotic behavior of the branches of the hyperbola. If we wanted a little more detail when drawing our sketches, we would use that, but we're just going to be concerned with rough sketches for our purposes here. Now, if we interchange the two terms in the equation of the hyperbola to y squared over b squared minus x squared over a squared equals 1, we get this hyperbola which has the branches facing in the other direction. Namely, they pass through a point on the y-axis. Okay, the first quadric surface we're going to look at is an ellipsoid. The standard form for an ellipsoid centered at the origin is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. As I said, we're going to sketch our quadric surfaces by looking at various traces. As a first step, we'll try to look at the traces in the coordinate planes themselves, and sometimes that will give us enough information to get a complete sketch. Sometimes we'll have to look at additional traces that are parallel to those coordinate planes. The ellipsoid is particularly simple. The trace in the xy plane, well, to find that, we simply set z equal to 0. And we get x squared over a squared plus y squared over b squared equals 1, which you should recognize as the equation of an ellipse in standard form. Similarly, the trace in the xz plane, x squared over a squared plus z squared over c squared equals 1, is also an ellipse. And in the yz plane, y squared over b squared plus z squared over c squared equals 1, another ellipse. So if we sketch the graphs of all three of these ellipses in the coordinate planes, we will get a nice representation of the ellipsoid. Okay, so I'm just going to label A, B, and C on this graph. We don't know what A, B, and C are. Let's assume that they're positive numbers so that A is on the positive x-axis, B is on the positive y-axis, and C is on the positive z-axis. I didn't label negative A, negative B, or negative C just to avoid unnecessary clutter. Let's look at that first ellipse in green there. We're going to graph that one in the xy plane. Notice how we move A units along the x-axis from the origin in both directions to get those vertices, and we move b units along the y-axis to get the other two vertices. We're going to do the same thing for the blue one, this time in the xz plane. Notice how we use A and C when sketching this ellipse. The vertices are at A along the x-axis and negative A, and the vertices along the z-axis are at C and negative C. And one more, when we sketch that red one in the YZ plane, we get this ellipse, which passes through B and negative B on the y-axis and C and negative C on the z-axis. By sketching these three traces, we get a nice three-dimensional picture of the ellipsoid. Next, we have a hyperboloid of one sheet. The equation of the hyperboloid of one sheet looks similar to the equation for an ellipsoid, except there is a minus sign. Just to be definitive, I put the minus sign in front of the z squared term. This will ensure that the hyperboloid is oriented along the z-axis. Once again, let's look at the traces in various planes. In the xy plane, we get x squared over a squared plus y squared over b squared equals 1. Again, an ellipse. In the xz plane, by setting y equal to 0, we get x squared over a squared minus z squared over c squared equals 1. And this looks like the equation of a hyperbola. And in the yz plane, we have y squared over b squared minus z squared over c squared equals 1. Again, another equation of a hyperbola. Okay, let's sketch these traces. This time, I'm only labeling A and B, because remember that C occurs after the minus sign. So that's going to tell us about the asymptotic behavior of the hyperbolas, but we're not particularly interested in that here. We don't need that level of accuracy. For the green one, that's an ellipse. It's graphed just like we did for the ellipsoid. Doing the red one next in the YZ plane, because it's a little easier to sketch graphs in the YZ plane than the XZ plane because it's flat against the screen. And we're just sketching the graph of a hyperbola that hits B on the y-axis as well as negative B. And here is the blue one. Notice this one gives it a little more three-dimensional look because it's coming forward and backwards from the origin, and it's hitting the x-axis at A and negative A. We want to finish by just closing off this hyperboloid just to get a nice section of it by drawing two more ellipses. Now, we get those ellipses by setting z equal to either a positive number or a negative number instead of 0, and we get two different ellipses which would be larger than the ellipse that we get from plugging in a z equals 0. You may want to check and verify that the ellipses get larger as you move upward along the z-axis from the origin or downward along the z-axis from the origin. I just want to mention that if we put the minus sign in front of the y squared term instead, then the hyperboloid would wind up being oriented along the y-axis. And similarly, if we put the minus sign in front of the x squared instead, the hyperboloid would be oriented along the x-axis. What characterizes the hyperboloid of one sheet is not where the minus sign is, but that there is only one minus sign when the right-hand side is equal to positive 1. Next, we have a hyperboloid of two sheets. The difference between a hyperboloid of two sheets and one sheet is that there are two minus signs this time. So we're going to do, again, the one that's oriented along the z-axis. So we have z squared over c squared minus x squared over a squared minus y squared over b squared equals 1. Okay, again, the fact that the z squared is the positive one ensures that it's oriented along the z-axis. Let's go ahead and do the traces again. Starting with the xz plane this time, if we set y equal to 0, we get the hyperbola z squared over c squared minus x squared over a squared equals 1. And if we set x equal to 0 to get the trace in the yz plane, we get z squared over c squared minus y squared over b squared equals 1. Again, a hyperbola. Now, setting z equal to 0 gives us x squared over a squared plus y squared over b squared equals -1. Notice we just had to do a little algebra there to bring the -1 over to the right-hand side of the equation after replacing z by 0. But this has no graph because the sum of two squares could never be negative in the real number system. So instead of using 0, let's look at the traces in the planes z equals c or z equals -c. Both lead to the same trace because we're squaring it. And notice we get c squared over c squared, which is 1. If we cancel out the 1s and bring the minus sign to the right, we see we get x squared over a squared plus y squared over b squared equals 0, which is just a point, specifically the origin. All right, so let's go ahead and sketch some of these traces, labeling the c and -c along the z-axis. First, notice that when z is plus or minus c, we get that x and y are both 0. So 0, 0, c and 0, 0, -c are both points on the graph. Let's do the red next because it's in the yz plane, which is a little easier to sketch than the xz plane. And we see that we have this hyperbola. Now, before I do the blue, which actually isn't necessary, it just gives a little bit more of a 3D look. But let's do a couple of more traces in the xy plane just to close up the top and bottom of this hyperboloid. If we set z equal to some number bigger than c, let's call it d, notice we get d squared over c squared minus x squared over a squared minus y squared over b squared equals 1. And just bringing the 1 over to the d squared over c squared and the x squared over a squared and y squared over b squared to the other side, we see we get x squared over a squared plus y squared over b squared equals d squared over c squared minus 1. Now, since d is bigger than c, the right-hand side will be positive. Whatever that number is, we could divide by it to put this into standard form. It's not particularly important exactly what it is, just that we recognize that we do get an ellipse, and that ellipse is going to look something like this. And we could use that to sort of just cut off the top of that hyperboloid to give us a picture of a portion of the hyperboloid. And similarly, if z is -d, which is less than -c, we get the corresponding congruent ellipse below the z-axis. And we already have a nice picture of the hyperboloid of two sheets. But if we want to add a little bit extra, we can go ahead and sketch the trace in the xz plane. And you could see that in blue there. Notice how that hyperboloid is coming forwards and backwards instead of going left and right because it's in the xz plane. I just want to mention that if we change the position of the minus signs so that the x squared is the positive one, then the hyperboloid would be coming forwards and backwards along the x-axis. And if the y squared term was the positive one, it would be going left and right along the y-axis. Our next quadric surface is the elliptic cone. The equation in standard form for an elliptic cone is x squared over a squared plus y squared over b squared minus c squared over c squared equals 0. We could also solve this equation for z to get z equals plus minus c times the square root of x squared over a squared plus y squared over b squared to have the elliptic cone in another form. Once again, let's sketch some of these traces. Let's start with the yz plane since it's flat against the screen. If we set x equal to 0, then we see that we get z is plus or minus cy over b. This is two lines that look something like this, right? The slope of these lines is c over b and -c over b, and they're both passing through the origin. For the xy trace, if we set z equal to 0, we get x squared over a squared plus y squared over b squared equals 0. This is just the origin. Just to look at some traces parallel to the xy plane, if we set z equal to some positive number d, then we get x squared over a squared plus y squared over b squared equals d squared over c squared by bringing that last term over to the right. And we see that we have an ellipse. Similarly, we get an ellipse below the xy plane as well if we choose some negative value to plug in for z. This is already a pretty decent picture of the elliptic cone, but for completeness, we'll look at the XZ trace, which is another pair of intersecting lines that are coming forwards and backwards instead of moving from left to right. Next, we have the elliptic paraboloid. The equation of an elliptic paraboloid, which is upward facing along the z-axis, is z equals x squared over a squared plus y squared over b squared. Let's look at some of the traces. To get the trace in the xy plane, as always, we set z equal to 0 to get x squared over a squared plus y squared over b squared equals 0. That's just the origin. Trace in the xz plane, we set y equal to 0 to get z equals x squared over a squared. You may recognize this as the equation of a parabola. And similarly, the trace in the yz plane, by setting x equal to 0, is z equals y squared over b squared, another parabola. First, graphing the yz trace, we just have our standard upward-facing parabola, z equals y squared over b squared. The trace in the xy plane is just the origin there. Now, if we take a trace parallel to the xy plane by replacing z by a positive number d, you could see that we're going to get an ellipse. So it will look something like this. And by the way, if we set z equal to a negative number, there won't be a graph because the sum of two squares cannot be negative. This is already a nice representation of the paraboloid. So just for completeness, we'll throw in this other trace in the xz plane, a parabola which moves forwards and backwards. Finally, we have the hyperbolic paraboloid. Its equation has the form z equals y squared over b squared minus x squared over a squared. Since z is by itself, this is going to be upward facing along the z-axis. And there are actually 6 possible orientations of the hyperbolic paraboloid. In addition to choosing which variable is by itself, we could also choose which variable on the right-hand side of the equation is negative or positive. Right, so we're going to be drawing an upward-facing hyperbolic paraboloid whose orientation is from left to right because the y is the positive part and the x is the negative part. Okay, so let's look at some traces. In the xy plane, when we set z equal to 0, we get y squared over b squared minus x squared over a squared equals 0. This just gives us the origin. In the xz plane, we get z equals negative x squared over a squared, which is just a downward-facing parabola. And the trace in the yz plane is z equals y squared over b squared, which is an upward-facing parabola. Okay, so let's sketch some of this. In the yz plane, we have this upward-facing parabola. In the xz plane, we have a downward-facing parabola. Note that this one is coming out and moving in as we trace out the parabola. Now, for the green, the trace in the xy plane just gave us the origin. That's not particularly interesting. So let's look at c values that are bigger than 0. In other words, let's look at an equation of the form y squared over b squared minus x squared over a squared equals c, starting with c greater than 0. In that case, we get a hyperbola whose branches look like the ones we have drawn in green there. Now, if c is less than 0, the hyperbola branches are facing the other way because in that case, we have to interchange the x and y to get the c to be positive. So our branches look as they do in the picture below the xy plane there. And now we could complete the picture just by drawing a few curves to finish this up. Here, 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 and here. And that gives us a nice representation of the hyperbolic paraboloid. Notice how the hyperbolic paraboloid is shaped like a saddle. And this is one of the 6 possible orientations. If it was x squared over a squared minus y squared over b squared, it would look like it was coming forwards and backwards instead of going from left to right. And then we could also make it oriented along the y-axis or x-axis, each in 2 other possible ways. Okay, let's try some examples. For each of these, See if you can classify which of the 6 quadric surfaces the equation is representing, and then draw a quick sketch of it. Pause the video now, try these yourself, and then resume the video to check your answers against mine. Okay, starting with 4x squared minus 3y squared plus 12z squared plus 12 equals 0. I'm going to bring the 12 over to the right to make it negative 12, and then divide by 12 to get x squared over 3 minus y squared over 4 plus z squared over 1 equals negative 1. We just have to get rid of that minus sign on the right. We could just multiply through by a negative 1 to get y squared over 4 minus x squared over 3 minus z squared over 1 equals 1. The two minus signs tell us that this is a hyperboloid of 2 sheets. Okay, it's oriented along the y-axis because the y squared term is the one that is positive. And of particular importance are the two vertices, which appear at 2 and negative 2 along the y-axis. The next one, x minus y squared minus 4z squared equals 0. Okay, just solving this for x, the term that is not squared, we have x equals y squared plus 4z squared. Because there is a term that is not squared, it's a paraboloid, and because both of the square terms are positive, it's an elliptic paraboloid. Okay, and it's going to be oriented along the x-axis because x is the term that is not squared. So it looks something like this. Finally, we have 4x squared plus 4y squared plus z squared plus 8y minus 4z plus 4 equals 0. Notice that this one has a y term and a z term, which didn't appear in one of our 6 standard forms. In order to get this to look more like one of our standard forms, we're going to have to complete the square twice, once for y and once for z. So let's start by grouping the x's, the y's, and the z's together. Notice how I moved the 8y next to the 4y squared and the negative 4z next to the z squared, and I brought the 4 over to the other side of the equation as a negative 4. Next, I factor out the 4 from the 4y squared plus 8y in preparation for completing the square. And now I go ahead and complete the square. For the y term, we have 2y. So 2 divided by 2 is 1. Square that to get 1. So I add and subtract 1 right next to each other inside those parentheses. For z, we have negative 4z. So half of negative 4 is negative 2. When we square that, we get 4. So I add and subtract 4. And now we have to recognize our perfect squares. Y squared plus 2y plus 1 is a perfect square. It's equal to the square of y plus 1. Now, what about that negative 1? To get that outside of the parentheses, we have to distribute that with that 4. So 4 times negative 1 is negative 4. And similarly, z squared minus 4z plus 4 is the perfect square, z minus 2 all squared. Finally, we want to bring all the constants to the right. We could actually just cancel out a negative 4 from each side. There's one negative 4 left on the left, so we move it to the right by making it a positive 4. Finally, we divide by 4 to get this in standard form. We get x squared plus the square of y plus 1 plus the square of z minus 2 over 4 equals 1. Notice that this looks like an ellipsoid, but there's some translation going on here. Right? So it's an ellipsoid, but the center, instead of being the origin, is 0, negative 1, 2. Right? The y plus 1 tells us that the y coordinate of the center is negative 1, and the z minus 2 tells us that the z coordinate of the center is 2. Okay, so when we graph this, make sure that we plot the center by moving 1 unit to the left and 2 units up. And from there, we could get the vertices. In the x direction, we move 1 unit from the center forwards and backwards. For the y direction, we move 1 unit from the center to the left and to the right. Right? For both of those, it's because they're both over 1. Even though the 1 doesn't appear, it's over 1. And for the z direction, we move up and down 2 units because the square root of 4 is 2.